Good afternoon, everybody. We have a lot to do today. So I know there aren't very many of us. Normally, we will kind of wait a few minutes and let folks roll on in, but we're going to get started because we need to go over chapter 6, and I've just got some practice problems for us to work through. And then we need to start chapter 7. So, yeah, lot to do. Lot to do. Hopefully, last week everyone was able to get a little bit of enjoyment out of that wellness day. That's why we didn't have class last week. We'll do as good of a job as we can with going over the concepts of chapter 6 using some practice problems. And then we'll move on to chapter 7. So your chapter 6 homework is not due until Sunday, just so you can have some time to kind of bring up your questions and things like that. So let's get started. For all of chapter 6, we're just going to do like learning checks and practice problems. And I'll kind of walk through it with you and make sure that we've got everybody covered. So this first one, we're looking at the element nitrogen. And hopefully you have a periodic table because you're pretty much going to need one here on out. We're going to step through A through D and answer some questions about the element nitrogen. First question, is nitrogen a metal or a non-metal? You can just put M or NM. Let me know what you think. Is it a metal or a non-metal? For those of you just joining us, we're doing some practice problems about chapter 6. Yes, it is a non-metal. Now, if you have your periodic table, you can look there and figure out how many valence electrons nitrogen has. When you figure that out, let me know what you think. How many valence electrons does nitrogen have? I'll give you a hint. Figure out what group nitrogen is in. Nitrogen is in group 5A. Remember, we care about the group number with the A after it. That tells us how many valence electrons there are. So if we had something that was in group 1A, it would be 1. Group 5A, there's 5 valence electrons. Part C. State the number of electrons that must be lost or gained to acquire an octet. An octet means, in most cases, we're talking about 8 electrons, okay? Oh, it's fine. If you don't have a periodic table, try to look one up real quick. Just Google it. Or you can look on, I think I posted one with Chem 104 on your in-course content. If you have access to the textbook, there's one on the inside front cover. Any periodic table will do. So a full octet means 8 electrons, 8 valence electrons. Nitrogen only has 5. So that means it needs 3 valence electrons. Or I'll put 3 electrons to have that octet. Now we've got to write the symbol including its ionic charge and name of the resulting ion. To figure out the charge of a nonmetal when it becomes an ion, you take the group number and subtract 8. So in this case, nitrogen is in group 5A, so it's 5 minus 8 gives us -3. That's the charge of the ion that nitrogen forms when it gains electrons. Now I don't remember if we mentioned nonmetals gain. So it needs to gain 3 electrons to become an ion. The symbol is N3-, and the way we name it, you start with the name of the element. We only want the first syllable. Get rid of everything else. Replace it with IDE. So that means the name of this is nitride. It is the nitride ion. So this steps through quite a few things from chapter 6, where we're looking at an element and how it forms an ion. We're going to do some more practice with this as we move through some more of the chapter 6 practice problems. Does anybody have any pressing questions so far, or are you ready to move on? Naming. We didn't get a chance to do any of chapter 6 in class. So I will do the first example, and then we'll talk about the other two. I'll let you have a chance to do them. We have a compound with iron. Iron is a transition metal. Whenever you're naming a compound, you have to identify whether or not, if it has a metal in it, is that metal a transition metal or not? Because with transition metals, you have to designate the charge using a Roman numeral. And we have to figure out that charge. So we know that the name is going to begin with iron because you name the cation first. You name the first element first. That's always a positively charged one. We don't know what the charge is, so I'll leave that to fill in. Then we have a nonmetal, which is oxygen. We take the first syllable of oxygen, which is ox, and then we add IDE because it is a negative ion. So that's almost the whole name, but we need to include the charge. Here's how we figure that out. Just like we did with nitrogen, we can figure out the charge of the oxide ion by taking its group number and subtracting 8. What group number does oxygen fall under? Which group is it in? So I have two answers. So it's in group 6A. The charge is going to be -2. The charge is 6 minus 8. And this is for oxygen. And any other 6A nonmetal. When we have an ionic compound like we do here, a metal and a nonmetal, that's an ionic compound, the overall charge has to be 0. So all the positive charge from the cation and all of the negative charge from the anion, when you add those charges together, it must be 0. In this compound, we've got 2 iron compounds, or 2 iron ions. So I'll say 2 iron, plus we've got 3 oxygens, and we know that the charge of those oxygens is -2. And our overall charge has to be 0. The charge from our oxygen is -6. We've got 3 of them. They each have a -2 charge. What does my iron have to be? What is the charge of the iron? You're pretty much solving this equation. Think of it as 2x minus 6 equals 0. Yeah, it's got to be 3. Is 2 times 3 equals 6. So we've got a positive 6 and a negative 6, and that equals 0. So the charge for each of the iron ions is 3 plus. So we put a 3 in Roman numerals in parentheses. I'll kind of help you walk through B and C. The first question, since we see it's a metal, aluminum, is aluminum a transition metal? You could put yes or no. Is it a transition metal? And remember that the transition metals are pretty much in the D block. On that periodic table. So aluminum is actually in group 3A. It is not a transition metal. It's a metal, but it's not a transition metal. So we don't have to name it using the Roman numeral for the charge because it can only have one charge. It only forms one ion. That's the reason why we use it's called the stock system, but the Roman numerals in parentheses, that tells us which ion we have. With aluminum, there's only one, so we can just call it aluminum. The second element is a nonmetal, and we name that by taking the first syllable, ox, and adding IDE. The third one, magnesium. Is that a transition metal? Correct, it's not. So we name this one by simply stating the element name, magnesium. Then we take the first syllable of the nonmetal. This is chlorine, so we take chlor and add IDE. So this one was naming ionic compounds. And again, I know this is going to be fast. Chapter 6 is a big chapter. We lost a day last week because of the wellness day. So we're trying to go through practice problems, and I'm trying to hit all the major topics in chapter 6 inside of about 30 minutes. We'll see how well we do. Any major questions about naming? I always post practice worksheets and the answer keys. The only way to do well with naming is to practice. So let me know if you have questions or if you're ready to move on. Yes. There are some exceptions. You're welcome. But we'll talk about that a little bit. So transition metals use a Roman numeral to designate the charge. Except for zinc, cadmium, and silver. Those only form one ion. So that's our rule. Okay. Other questions? Okay. I'll take that as a no. We're going to do some more. This time we're taking the name and writing the chemical formula. Do you want me to go through these, or do you want the opportunity to try them yourself? Yeah. So I'll do the first one, and then y'all can try the other two. We're still working with ionic compounds. Ionic compounds have a metal and a nonmetal. The name nickel 2 sulfide gives you a lot of information. Nickel 2, that's the cation. The metal is always positively charged, and a cation is a positively charged ion. The sulfide tells you the identity of the anion. We'll work with the cation first. Nickel is the metal. Its symbol is Ni. The Roman numeral 2 in parentheses tells us what charge it is. For the anion, we have to do a little bit more work. The first syllable of this word is sulf. That comes from the element sulfur. But this name doesn't tell us what the charge is. For that, we have to go back to the periodic table. What group is sulfur in? It's in group 6A. So our charge is going to be 6 minus 8, which gives us minus 2. If I were to have one of the nickel ions and one of the sulfide ions, my overall charge would be 0. That means that my chemical formula will have 1 nickel and 1 sulfur. And I'm done. I'll give you 2 minutes to try B and C. I'll give you a warning that with C, you're going to have to figure out for both B and C, it's not going to be as simple as, oh, just 1 and 1. You're going to have to balance the charge. Would you like me to show you an example of balancing the charge? Okay, I figured. So again, the first word is zinc. That's our cation. Zinc is a transition metal, but it's one of our exceptions. It only forms 1 ion. So whenever I see zinc, I think zinc 2+. For the anion, chloride. Chlor comes from chlorine. That's Cl. What group is chlorine in? It's in 7A. So our charge is 7 minus 8, which is -1. If I just had 1 zinc ion and 1 chloride ion, I would not get 0. I'd get a +1. So I can't just have 1 of each. What I have to do is kind of this swapping method. I'm going to take the charge of the zinc, which is our cation, and use that as the subscript for my chloride ion. I now have 2 of them. Now I'm not going to do that for the chlorine because the charge there is only 1 minus. I don't write a 1 for a subscript. So we just leave the zinc alone. But then we check again for our charge. If I had 1 zinc ion and 2 chloride ions, now, whoops, I wrote the 2 instead of a 1, getting too excited here. Okay. Now I'm balanced because I've got 1 positively charged ion, that's +2, and I've got 2 chloride ions that each have a charge of -1, which makes -2. So my formula is ZnCl2. Take a minute and try C. We won't have a whole lot of time for you to finish every single problem, but it's valuable to at least get started and see if you get stuck or, given time, I think I could finish this. So that's really the goal with Chapter 6, is to see the major points where you need help, try to give you that help, and then we move forward. I'm going to get started on this one. We've got iron 3 oxide. The cation is first, and the Roman numerals tell us the charge. Iron is Fe, The 3 in parentheses means 3 plus. Easy. Oxide, we've done that before. It's in group 6A. So the charge for the oxide ion is going to be 2 minus. If I just had one iron and one oxide, it absolutely would not be 0. So I have to do my swapping deal. And since both of the charges are greater than 1, I'm going to have to swap for both of these. I'm going to take the 3 and drop it down as my subscript for the oxygen. I'm going to take the 2 and drop it down as my subscript for the iron. Now let's double check that. I have 2 iron ions that have a charge of 3 plus each. I've got 3 oxide ions that are all -2 each. That's a +6 and a -6. So that means our formula checks out. And that is the formula for iron 3 oxide. So how do we feel about these? Mm-hmm. We ready to move on? So now we're going to identify a compound as ionic or covalent. And what I want you to do, since we've already done some naming of the ionic compounds, I want you to name the covalent ones. So as a quick reminder, ionic means you've got a metal plus nonmetal. Could be more than one nonmetal, but you see a metal there. Covalent means you've only got nonmetals. So let's go through these together and state whether they are ionic or covalent. You can put an I for ionic or a C for covalent. Letter A. Is this compound ionic or covalent? It's covalent. Remember that the nonmetals are like the upper right quarter of the periodic table. Letter B. Ionic or covalent? I agree. it's ionic. Ba, that's barium, that's a metal. So if the first element is a metal, it's going to be ionic. Now C is a little bit of a tricky one. And the reason is NH4 is a common polyatomic ion, and it's one of the exceptions. So if you see the ammonium ion or a metal, then it's going to be ionic. You will not need to memorize the ions. I will give you the chart from chapter 6 that has all of the polyatomic ions that you need to recognize. So if you didn't memorize them, don't worry. You don't need to. You just need to know how to recognize them and use the chart. Letter E. Ionic or covalent? It's covalent. I'll walk you through how to name the covalent ones. The first word of the name is going to reflect the element name, the first element that you see. So that's going to be sulfur. If there were more than one sulfur atom, then we would include that using a prefix. But there's only one, so we just write the name. Next, we have to describe the oxygen, and there are 3 of them. So we're going to use the prefix tri, and that means 3. The first syllable of oxygen, which is ox, and then we add IDE. I'll name the next one too. So letter E we said was also covalent. The first element is nitrogen. I'm going to try to keep it as black here. And we see that there are 2 of them because of this subscript. So we need to use a prefix that means 2. That prefix is di. So these prefixes, mono, di, tri, you'll need to know these. And you know most of them already just from living life. So we've got our prefix. Then you name the element, nitrogen. Next, we have to name the oxygen portion. 4 is tetra. Then we use the first syllable of oxygen, ox, followed by IDE. Now, since we have an A next to an O, we got to do something about that. Tetraoxide, it's a little bit awkward. And your exam is not a spelling exam, it's multiple choice. So you'll be okay there. But the rule is you get rid of the first vowel if you have 2 vowels right next to each other. So we get rid of the A. again, small detail. I wouldn't even worry about putting it into your brain. As long as you recognize you need tetra, then you'll be able to get the right answer. So let me know how we're doing with naming covalent compounds. Does it make sense? And again, I know we're going fast. We have ground to make up because we didn't have class last week. So if you didn't get a chance to watch the Chapter 6 videos, Chapter 6 is going to be a struggle. And this section of lecture is not going to be helpful to you because you won't already have the background. All right. So all that we covered was naming, writing chemical formulas, ionic, covalent. Now we need to talk more about covalent molecules and the different ways that we can categorize them. What I've done is I've made a summary table, and this table will be very helpful to you with your homework. Because with a lot of the questions, you'll need to answer questions about the molecule polarity and shape, number of lone pairs, bonded atoms, all that kind of stuff, bond types. So it puts all of that together in one table. Let's walk through a couple of these just so that you know how to use the table. When we're looking at a linear molecule, we're talking about something like oxygen. So that's O2. It's got some lone pairs as well. We're not really concerned about those. The type of bond is nonpolar. The way you figure that out is by looking at the electronegativity differences. Electronegativity is just a way to say how much an atom wants to take electrons from something else. So all of the nonmetals have higher electronegativity than all of the metals because the nonmetals gain electrons to form ions. And metals, they don't really want to gain electrons. They want to give theirs away. So they're going to have lower electronegativity. The bigger the difference between the atoms in a compound or a molecule, then you're going to go from a nonpolar to a polar bond. And if the difference is that great, it's going to be ionic, like in the case of table salt, NaCl, where you have a positive ion and a negative ion. And that's electron transfer. So that's electronegativity in a nutshell. How much does a particular atom want to gain electrons? Depending on how all of those bonds in the molecule are arranged, you can have overall polarity of the molecule be nonpolar, even with polar bonds. Our example of this is carbon dioxide. The electronegativity difference between the carbon and the oxygens is high, so that there's a partial positive on the carbon and partial negatives on the oxygen. The oxygens the electrons in that molecule are hanging out more with the oxygens than they are with the carbon. But it's balanced out. You've got electrons on one side, electrons on the other. So overall, this molecule is nonpolar. So that's how you can kind of use this chart. I feel like the shapes and the polarity and things like that, because they're so abstract, this chart will help you. So if you can figure out one part of the chart, say you know that something has nonpolar bonds, then you can look at the bond type and figure out, okay, what are my options? Can I have, my molecule, is it going to be nonpolar or polar? So you'll just have to practice using this chart. But I want to go through some examples with you to show you how to use this information. So if you're a little bit lost still, don't worry. Hopefully working through some examples together will help you. So one of the questions you're going to see on your exam is asking about the polarity of a molecule. In this example, we have PBr3, which we can name. It's phosphorus, tribromide. It's a covalent molecule. You name the first element. You use a prefix, the first syllable, then IDE. Okay. We have to talk about whether or not this molecule is polar or nonpolar. The first thing we have to do is figure out, do we have polar bonds or nonpolar bonds? On the right, on the left, we've got the electronegativity table. That's phosphorus. That's bromine. The difference in electronegativity between these two is equal to 0.7. Now, I don't have it listed here, but in the Chapter 6 lecture, the difference in electronegativity between two atoms, there's different ranges for the different bond types. 0.7 falls under polar covalent. So those are the bond type that we have. Next thing we have to do is figure out the geometry of the molecule. So let's start writing some steps down. First thing we did was identify the bond type. We did that by using the electronegativity table. You'll be provided with that information on the exam. You don't need to memorize these. The second thing we have to do is figure out the shape of the molecule. To do that, we have to use Lewis structures. We draw the structure for phosphorus. It's in group 5A, so it's going to have 5 valence electrons. Bromine is in group 7A. It will have 7 valence electrons. Now we've got to put 3 bromines with our phosphorus. I'm going to pause here. Are there any questions about figuring out the difference in electronegativity or how to draw the Lewis structure for a molecule? Because those are the two things that we just did. If you're like, this is fast, I don't get it, let me know. I can't just take this time to go over chapter 6, but I'll at least know where we stand so I can make sure that I can kind of fill in the gaps throughout the rest of the semester, because you'll need this information for the final. So speak up. Let me know how it's going. All right. So we are still identifying the molecule shape. We figured out the Lewis structure, and now we need to figure out how to call the shape for this molecule. In this molecule, we have 3 bonded atoms, and we've also got 1 lone pair. I'll circle the bonded atoms in red. That's our bonded atoms. And the only lone pairs that we care about are the lone pairs on the central atom. We don't care about the ones on the bromine. They don't contribute to the shape of the molecule. Then we look at the chart and figure out what shape we have. I've got 3 bonded atoms. So that means that I could have this or this for our molecule shape: trigonoplanar or trigonopyramidal. But I've also got a lone pair. So that rules out trigonoplanar. Has to be trigonopyramidal because I've got 3 bonded atoms and 1 lone pair. So what that looks like is like this. Since we have polar covalent bonds, that means we're going to have dipoles. The phosphorus is going to be partial positive, and all the bromines are going to be partial negative. When we look at the dipole moments, which means just where are the electrons? Are they kind of spread out evenly over the molecule, or are they hovering in one area more so than another? They're hovering more in one area than another. So that means this molecule has to be polar. And that's because it's got polar covalent bonds, and the shape of the molecule does not make any of that cancel out. So I know we went through several steps here to get to the answer. If you can skip some of these steps if you understand it, but I wouldn't skip over identifying the bond type for sure. If you can go straight from the bond type and looking at the molecule to the molecule shape without drawing the Lewis structure, that's fine. But you need to know the shape. So I did 2.8 minus 2.1 because I've got bromine and phosphorus as part of my bond. So I've got 3 bonds, and they're all between phosphorus and bromine. So I figured out the difference in electronegativity between those two elements. You're not going to have a negative electronegativity. Does that help? Okay. So for completion's sake, let me write the third step that we did, which was determine polarity. This type of problem encompasses a lot of what I talked about in the second video for chapter 6. That's why I chose to do one of these problems. Any other questions on this slide? I'll take that as a no. We're already well past the 30 minutes I was hoping for, but I just can't leave chapter 6 completely alone. I feel like that would be super unfair for you to have an exam on it when we didn't even do any practice problems together. Okay. The other part of that second video that we need to talk about is intermolecular forces. And I like this table because it summarizes bonding forces and intermolecular forces. So bonding forces, we're talking about between atoms or ions. If we're looking at intermolecular forces, it's between molecules. The forces between atoms or ions is much stronger than the forces between molecules. And that's demonstrated on this chart. You'll definitely need to know the relative order from weakest to strongest in terms of the bonding and intermolecular forces. One thing that some folks miss is the difference between dispersion forces and dipole-dipole attractions. They're both pretty weak. But dispersion forces are usually reserved for compounds where you have two of the same element. So those diatomic molecules, like N2, O2, F2, all of the elements that naturally are found paired up, that's what dispersion forces describe, the interactions between these molecules. Dipole-dipole attractions, we're talking about things where you have still two nonmetals, but they're two different nonmetals. So the example here is hydrogen and chlorine, where you have a positive, a partial positive, and a partial negative. And that's because of the differences in electronegativity. So within the molecule, you've got a difference in electronegativity that causes a partial positive on one end and a partial negative on the other. With dispersion forces, we're really just talking about temporary dipoles where a molecule knocks into another one and it shakes some electrons over one way and the nucleus another way. So very slight differences in the definitions of these two different forces, but you need to understand the difference. The third one for intermolecular forces is a hydrogen bond. The only elements that form hydrogen bonds are nitrogen, oxygen, and fluorine. Best way I can give you to remember that is having FON with hydrogen bonds. And that will remind you only these three elements form hydrogen bonds. So that's a very quick overview of this chart, but it is a good one to have in your notebook. Now we're going to practice using it. We've got to identify the main type of intermolecular forces that are present in liquids of the following compounds. For part A, we've got water, H2O. So the types of bonds that we have, it's going to be an oxygen bound to a hydrogen. That's a hydrogen bond. Because the bonds in the water molecule are hydrogen bonds, and the way that those molecules will interact with each other is also hydrogen bonding. Letter B, we've got two of the same element, and they're both nonmetals. So that means it's going to be dispersion forces. KCl. K is potassium. That's a metal. So your mind should instantly go to ionic. The third one, we've got nitrogen and hydrogen. Nitrogen can also do hydrogen bonding. So hopefully if there were some question marks there, that this helped clear it up a little bit. Questions about this? Okay. Then that means it's time for Chapter 7. But before we do that, we'll take a short break. Take 5 minutes. We'll come back at 3:05. Then we'll start Chapter 7. So I'm going to start recording now. We're done with break. I will answer questions about the exam. So the test closes on Saturday at 11:59. So let's just go over these details. We have exam opens today at 5 p.m. Closes on Saturday at 11:59 p.m. I posted a practice exam that's about 10 questions or so. You don't have to do it, but the practice exam has some sample multiple choice questions across all 3 chapters that will be represented on this exam. So I highly recommend that you take advantage of it and do it. Try it like an exam and see how it goes. That will help you know what you need to focus your studies on the most. Are there other questions about the exam? As usual, I will post an exam folder. This is exam 2. So it'll be exam 2 folder, and it'll have a periodic table, and the ions chart. There were no equations from this section, so there isn't going to be an equation sheet. You're just going to have those 2 references. What I recommend you do is practice making a periodic table cheat sheet that has your periodic trends, and if you need help with doing all the configurations, some of that information too, like labeling all the different sublevels. When it comes time to take your exam, you have your printed, fresh copy of the periodic table and your ions chart. Start the exam in Respondus, and then recreate your cheat sheet right there in the session. I do not put a time limit on the exam, so you can take a little time to make your cheat sheet without your notes. But you can, anything you pull from your brain, you could put down on that paper. I recommend you do that and use it as a reference while you're taking the exam. I'll put out an announcement when the exam is posted, and I'll also put out a reminder sometime tomorrow to say, hey, don't forget, exam is going to close. So if you need emergency office hours, please let me know ASAP. If you do not tell me before the end of class, before I log off, which I linger for a couple of minutes, then chances are I will not be able to do it for you. All right. So with that said, we're going to start chapter 7. I know, it's kind of tight. You got an exam on chapters 4 through 6, and you're supposed to pay attention in class on a chapter that you're not being tested on yet. It's a little bit rough, and I'm sorry. Semester is a little shorter. We've lost a couple of days, so I can't just say, well, just go study, y'all. I wish I could. Instead, we're going to try to power through some of chapter 7. I understand you may not have watched the videos yet, but they're all there for the whole chapter. We're not going to cover the entire chapter today. We don't have time. But we're going to try to get through what I've set up here. And whatever we don't finish, we'll finish next week. In the meantime, try to watch those videos. If you didn't finish watching the chapter 7 videos, or you haven't even started, watch them before class next week, because it will make next week's class a lot more helpful, and you can do the practice problems and see where you stand. All right, enough of that. We'll get started with the actual material. First section, we're talking about equations for chemical reactions. Quick review of what a chemical reaction is. It's a chemical change. We talked about chemical changes in chapter 3. But we're bringing it back up in chapter 7. A chemical change is when a substance is changed to another substance. It's got a different formula, different properties. There's several ways that you can observe a chemical change, and it may be by the formation of bubbles, change in color, you produce a solid when you didn't have one initially, or a change in heat. Your reaction vessel gets hot or it gets cold as the reaction progresses. You don't have to see all of those changes for there to be a chemical reaction. Just one will do. Went into more detail in the Chapter 7 video. We're not going to go into it here. I think this is something that you guys understand. These are the symbols we'll use to write a chemical equation. You always have the reactants on the left-hand side, an arrow, which means reacts or yields, produces, and then your products on the right-hand side. When you have more than one reactant or more than one product, they're going to be separated by a plus sign. The other bit of information that you need to have when you're writing an equation is the state of matter. Solid, liquid, gas, aqueous. Aqueous just means dissolved in water. So we need to know what state the compound is in. Otherwise, you can't really do that reaction. Another piece of information that is nice to know is whether you have to heat the reactants. If they're heated, then you'll see this little triangle. It's the delta sign. So that means heat. You put the triangle over top of that arrow. If chemical equations and writing equations is kind of not your thing, you don't remember it from chemistry, I'd put this chart in a notebook somewhere and have it handy, just so that you can kind of keep an idea of like, okay, I need to make sure all of these things are in my equation when I'm writing it out. The reason why we're talking about what an equation looks like is because we're going to have to balance equations. And the goal of balancing an equation is to have the same number of atoms on the reactant side as the product side for each element. So this is our goal. The picture on the right just shows the same number of hydrogen atoms and oxygen atoms on both sides. That's the goal. Same on both sides. So I'm going to give an example of how to balance. Oh no, this one is balanced already. What we need to do is count the number of atoms of each element on the reactant side and the product side. I'm going to set up the table that I use, and then I want you to fill it in. So I will usually draw a table like this that has each of the elements that I see written down the first column here. So I see aluminum, iron, and oxygen. I have a column for the reactant side, which I label with an R, and a column for the product side. I label with a P. Then I count the number of atoms for each element on the reactant side and the product side, and I fill it in. I'll give you a couple of minutes. I want you to take a look, try to fill it out yourself, and then I will come in and fill it in. Okay, you guys can help me fill in the chart. Aluminum. How many aluminum atoms do you see on the reactant side? There's 2. The 2 out in front means that you've got 2 of whatever that follows. So there's 2 aluminum atoms. Next we have the iron. There's a subscript of 2 there, which means that we've got 2 of them. The oxygen also has a subscript of 3. So there are 3 oxygen atoms. If this equation is balanced, we should have the same number of atoms on the other side. We've got 2 irons, 2 aluminums, and 3 oxygens. This equation is balanced. And that's how you count the number of atoms of each element on each side. So just by a brief poll, for the remainder of this class, do you want me to just go through the examples? Okay, then that's what I'll do. I'll go through the examples. You know I like feedback. So every once in a while, I'm going to just be like, hey, y'all, we living? We still here? And just appease me and let me know you still there and you're all right. So we'll go through this. I'll show you some things, point some things out. And then hopefully next week, when there isn't an exam, we can come together, do some practice problems related to what we covered this week, and move on with Chapter 7. So that's our goal. Okay. First major thing you'll need to do in Chapter 7 is balance equations. That means getting the same number of atoms of each element on both sides. We're going to start off by doing the same thing I just did. Figure out how many atoms of each element we have on the reactant side and the product side. The subscript after the iron tells me that I have 2. The subscript after the oxygen tells me I have 3. There is no subscript with the carbon, and we don't see a coefficient out in front. That means we've only got 1. Product side, we've got 1 iron, 1 carbon, and there's a subscript here for the oxygen that tells me I have 2. Clearly not balanced. This is our first table, just to take a lay of the land. Now we've got to decide how we want to balance this. You always want to go with kind of the most complicated, the one that has the biggest difference. 3 and 2, very not different. Typically starting by balancing your oxygens is a good place to start. You find the lowest common denominator, which is 6. So you can take 6, divide by 3. You can take 6 and divide by 2. It's the smallest number that you can do that with. That's what the lowest common denominator is. To get to 6 on the reactant side, we're going to place a 2 in front of the compound that has oxygen. To get to 6 oxygens on the product side, we're going to place a 3 in front of where we see oxygen. Notice that I did not change the subscripts. Don't change them. That would change the compound. Instead, you add coefficients. And those coefficients are in front of the compounds. So we made some changes. Now we need to make another chart. This will tell us what's balanced, what still needs to be balanced. We placed a 2 in front of this iron oxide compound. That means that we now have 2 times 2, which is 4 iron atoms, and 2 times 3, which gives us 6 oxygen atoms. Haven't touched the carbon, so there's 1. Product side, we haven't touched the iron, so there's still 1. The carbons, however, there are 3 carbon dioxide molecules, which means we've got 3 carbons, and 3 times 2 is 6 oxygens. Our oxygens are balanced, but the iron and the carbon, they're not. Lowest common denominator for the iron is going to be 4. That means we're going to place a 4 in front of where we see the iron on the product side. We're also going to do carbon in the same fell swoop because it's pretty easy. We've got 1 on the reactant side, 3 on the product side. Lowest common denominator is going to be 3. So we fill that in as well. Do a final chart to check. Double check your math. Make sure everything really is balanced. Four, 3, and 6 we have for iron, oxygen, and carbon on the reactant side. And we have the same on the product side. So that means we are balanced. The question is asking for you to list the coefficients in order from reactants to products. So you're just going to give the numbers in front of each of these compounds, starting at the far left and going all the way to the right. So that's 2, 3, 4, 3, which is B. On the homework and on the exam for Chapter 7, you're going to have to state what the coefficients are. So get used to doing that. It could be a question of, what is the coefficient for carbon in this balanced equation? And you would say 3. So those are the types of questions you'll see for balancing equations. I'm going to save this question for next week because I want us to have something to practice. So don't worry about this one. We're going to save it, and it's going to be one of the ones we start with next week. Chemical reactions. We have to talk about the different types there are. You'll need to identify chemical reactions. This is the list that we have. Combination, decomposition, single replacement, double replacement, combustion. 5 types. I'll write on here kind of the overall what these are. In the video that's posted for Chapter 7, I go into a little bit more detail. I had different slides for each one of these. Not going to do that here. Combination reaction, you're taking two or more simple substances and creating one complex product. Multiple reactants, one product. That's how you can identify this. A decomposition reaction is very similar. It's just the reverse. You have one reactant and it breaks down or decomposes to form multiple products. Single replacement reactions, what we're talking about here is metals usually. Some metals are more active than others, and they can replace a metal in an aqueous solution. So if A is a metal and it's added to a solution of BC, if it's more active, it will end up in the solution. The less active metal will precipitate out. And what that means is it's going to form a solid. The highlighting is to help you keep track of what's where. So let me give a color to the C as well. Double replacement reactions are kind of similar to single replacement, but instead of one swap, we have a double swap. And we've got two aqueous solutions. You're taking them, you're mixing them together, and A and C switch places. Okay. So to give you a written description, the positive ions swap partners. I don't know if this show is on anymore, but there used to be a show called Wife Swap, which I thought was utterly ridiculous. Why would you want to switch spouses with somebody? The check can't be that good. But that's essentially what's going on with the double replacement reaction. the positive ions are swapping partners. In this case, you form two new substances, one of which is insoluble. So you form one insoluble substance and one new aqueous solution. And I abbreviate solution SOLN. The final reaction type is combustion reactions. You have a carbon-containing substance. You have some oxygen gas. You add some heat. You make carbon dioxide, water, and lots of energy. This reaction should be familiar to you because if you've ever driven in a vehicle, car, bus, motorcycle, whatever, chances are it's probably fueled by gasoline or diesel. Those are carbon-containing compounds that, when mixed with air that contains oxygen, they combust and create emissions like carbon dioxide and water and a lot of energy. And that energy is what propels your car forward, okay? So when you think about a combustion reaction, think about a car engine. You'll need to identify reaction types based on these descriptions. Is everybody still with me? There's a lot on this slide. So let me know if you're still, at least if you're still here. Thank you. So I'll go through and label these and show you the kind of logic you'll need when you're answering a question like this. So we've got 4 reactions and we have to identify them as one of the 5 reaction types that I detailed on the last slide. First reaction in A. We've got a metal over here and we see an acid, which is an aqueous solution. On the other side, we see that the metal is part of the aqueous solution now, or it's a solid, right? So we've made something different, and we've also made hydrogen gas. This is going to be a single replacement because we're only doing one thing, right? We don't have multiple aqueous solutions. Single replacements are usually with a metal and something aqueous. B, we've got 2 aqueous solutions, and we form something that's insoluble and a new aqueous solution. So this is going to be a double replacement. We can look at where the positive ions are. So they've swapped partners. That's how you know you have a double replacement, because you have two different things swapping. In C, we've got multiple reactants and one product. That's a combination reaction. In D, I see something with carbon, I see oxygen, I see energy being produced. It's got to be combustion. That's the kind of question you'll have with your homework and for your exam, to identify different reactions. That was 7.2 in a nutshell. Now we need to talk about oxidation reduction reactions, which I abbreviate redox. So if you hear redox, that's what that is, oxidation reduction reactions. Redox reactions can fall under any of those categories. It's just another facet to the reaction types that we talked about. Some of them are redox as well as single replacement, for example. With a redox reaction, we're talking about transferring electrons from one substance to another. One way that you can remember the difference between oxidation and reduction is using this mnemonic oil rig. Oxidation is loss of electrons. Reduction is gain of electrons. I personally am more of a fan of Leo the Lion says grr. Lose electrons, oxidize, gain electrons, reduce. It's a little silly, but that's how I learned it all those years ago. I mean, like high school, and it still sticks in my head to this day that Leo the Lion says grr. So you choose if you need a little mnemonic to remember which is which. But you need to know oxidation, loss of electrons, reduction, gain. This chart is also really handy because it summarizes not just what oxidation and reduction are, but the way that it might look in a chemical reaction. So oxidation may be adding an oxygen or losing a hydrogen, and reduction might be loss of an oxygen or gain of a hydrogen. So I'd recommend putting this one in your notebook. It'll help you out. What you'll need to do with that information is identify whether or not something is being oxidized or reduced. You may have an equation like an A where you have a metal that is losing its electrons. When you're losing electrons, you'll see it on the product side. Lose electrons, that means you're oxidized. Whoops. So that's an oxidation reaction. In B, we've got our electrons on the reactant side. So that means we're gaining electrons. We're going from iron 3 plus to iron 2 plus. That's a reduction. In C, we're going from a molecule, which has 0 charge, and we're adding 2 electrons. That means we're gaining electrons, and it is again a reduction. Electrons on the reactant side, more than likely what you're looking at is some kind of reduction. If you have electrons on the product side, however, that means that you're releasing those electrons, you're losing them. That's oxidation. You won't always see these half reactions like this. It may be a chemical reaction, and you need to identify which element is being oxidized and which one is reduced. I'll try to make sure we do an example like that in class next week. Okay. We have a bit more to go, but I want to give you another 5 minutes just to kind of breathe, woosah, catch up, shake your brain out, whatever you need to do. So take another 5 minutes. It will be back at 3:50. All right, it's 3:50. Hopefully you had a chance to kind of shake your brain out a little bit. We're going to go ahead and get started. The first 3 sections of Chapter 7 are kind of like their own thing, talking about how to read a chemical equation and balance it, classify chemical reactions. Now we're getting into the quantitative stuff. So what can we do with those reactions? Before we can start, calculating how much product we'll make or anything like that, we need to learn about the mole and some of the other things we can do, basic calculations with the mole. When we're counting really small particles like atoms, molecules, and ions, we use a unit called the mole. And a mole is defined as 6.02 times 10 to the 23rd items. So that items could be atoms, molecules, or ions, any of those. It's a big number, but when you think about it, atoms and molecules, they're super duper tiny. So we're saying 1 mole is 6.02 times 10 to the 23rd items. That's an equality that you'll need to know. You will not be given that equality. That's something you will need to know cold. We can use Avogadro's number, which is the mole, as a conversion factor. Yes, conversion factors are back. If Chapter 2, when we did the metric conversions and like percentages and that kind of stuff, if that was difficult for you, then you need to get caught up and be ready for Chapter 7 because we're using conversion factors again. Office hours, upswing, help each other out. If you don't have a group me already, get one going. Study virtually together. Okay. If our equality is 1 mole is equal to 6.02 times 10 to the 23rd particles, then we can write two conversion factors. 1 mole over Avogadro's number, and then Avogadro's number over 1 mole. Those are our two conversion factors. Here's an example of how to use Avogadro's number. How many carbon dioxide molecules are in 0.5 moles of carbon dioxide? I always like to rewrite the question. We're given 0.5 moles, which I abbreviate mole or moles as MOL. It's a very chemistry thing to do. Your book doesn't really do it, but oftentimes other more traditional chemistry textbooks will. We're trying to figure out how many molecules are in 0.5 moles. The problem type that this is moles to molecules. For our equality, we're always going to use 1 mole is equal to 6.02 times 10 to the 23rd. In this case, we're talking about molecules, so we'll say molecules. The conversion factors, 1 mole over 6.02 times 10 to the 23rd, molecules, and the reciprocal. Then we set up the equation. Starting with our 0.500 mole of carbon dioxide, we have to choose which conversion factor will get us from moles to molecules. Moles are already in the numerator, and we're trying to cancel them out, which means that we need to have a conversion factor with moles in the denominator. You'll also need to refresh yourself on writing things in scientific notation and entering them into your calculator. Sig figs are also coming back. We've got 3 sig figs here in our 0.500 moles, so our answer needs to have 3 sig figs. You multiply 0.5 times 6.02 times 10 to the 23rd. And this is what you get. 3.01 times 10 to the 23rd molecules. And that's with 3 sig figs. I know y'all have the exam for chapters 4 through 6, but I'm trying to give you a heads up for the stuff you'll need for chapter 7 to kind of catch up and be ready. I'll do one more just to give you an example. We need to figure out the number of atoms in 2 moles of aluminum. anytime you're going from moles to number of things or number of things to moles, you have to use Avogadro's number. We want moles to cancel out, so 1 mole goes in the bottom. Avogadro's number goes in the top. When you do the multiplication, this is what your calculator will tell you. But we can only have 2 sig figs. That leaves us with 1.2 times 10 to the 24 aluminum atoms. And that's C. We can use moles to talk about the relationships of the number of atoms in a formula. So we can say there's 9 carbon atoms in aspirin, let's say, 8 hydrogen atoms, and 4 oxygen atoms. But we can also say 9 moles of carbon, 8 moles of hydrogen, 4 moles of oxygen. So that's how we can look at a chemical formula and the subscripts. We can use those subscripts to write conversion factors. If I have 1 mole of aspirin, which is C9H8O4, I also have 9 moles of carbon. So we're taking this 9 here, and instead of saying 9 atoms, we're saying 9 moles. We can do the same thing for each of the elements in aspirin. If I have 1 mole of aspirin, it contains 8 moles of hydrogen. It also contains 4 moles of oxygen. Because they're conversion factors, we can also write the reciprocal. So I'm going to pause here and just check in. Let me know you're still kind of with me, even if it's not all sinking in. It's fast. In Chapter 7, so Chapter 6 and Chapter 7 are big chapters. And I could probably spend 3 weeks on Chapter 6 alone. But we don't have that type of time. I could spend a solid 2 weeks on Chapter 7. But we don't really get that either. But the key for Chapter 7 is to do practice problems. So I implore you, I know you have your Chapter 6 homework due on Sunday, but make sure you watch the videos for Chapter 7 before we have class on Thursday. Otherwise, it is just going to be a wash. If I don't want to tell you don't come to class, because that's bad. But if you don't watch the Chapter 7 videos and already have some introduction to what we're doing, then the class time will be far less productive for you. So make it worth your while. So we've got these conversion factors, but we have to practice how to use them. If we know how many moles of an element are in a particular compound, then we can use that to make calculations about how many atoms and eventually mass, so grams. But that's coming in the next section. So we've got how many atoms of oxygen are in 0.150 moles of aspirin. First thing you need to do is rephrase the question. Here we're going from moles to atoms. But it's not moles to atoms of the same substance. We're going from moles of substance A to atoms of substance B. So we actually need to do two things here. The first is to figure out how many moles of oxygen we have. Once we know how many moles we have, we can use that along with Avogadro's number to go to atoms. For our first equation, the first part of the equation, we have to write conversion factors from the formula for aspirin. There are 4 moles of oxygen for every 1 mole of aspirin. And again, we get that because of that 4 there. And then, of course, we have the reciprocal. For the second part, we need Avogadro's number. And the 2 conversion factors we can write there, 1 mole of oxygen has 6.02 times 10 to the 23rd atoms. And we can write the reciprocal. Then we set up our equation. We're starting with the number of moles of aspirin. And with our plan, we said we're going from moles of aspirin, and our first conversion factor should get us to moles of oxygen. Moles of aspirin, that's in the numerator. We're trying to get rid of it. So that needs to be in the denominator of our conversion factor. The next part of the equation needs to take the moles of oxygen and convert to atoms. So here we're trying to get rid of moles and replace it with atoms. That means moles has to be in the bottom. Getting to this step is the hardest part. Once you get here, putting the numbers in is trivial into your calculator. But if you set up your conversion factors wrong, then you're not going to get the right answer. Let's double check our units. The first conversion factor, we get to moles of oxygen, and that's what we wanted. Our second conversion factor, we get to atoms. So we're good there. So you're going to multiply 0.15 times 4 times 6.02 times 10 to the 23rd. When you do that, you should get 3.61 times 10 to the 23rd oxygen atoms. I would encourage you to go back and kind of try these in your calculator. You don't even have to watch the video if you don't want to. You just look at the notes and make sure that you can put it into your calculator and get the same answer. Okay. We're going to save this example for next week. So we'll have a balancing and one of these where you have to write some conversion factors and go from moles of something to atoms of something else. Okay. So what have we covered so far? A lot is the answer. We talked about writing equations, balancing equations, types of chemical reactions. We also talked about redox in there. We just introduced the concept of the mole. Now we're adding to that. We have molar mass. The molar mass is just the quantity in grams that equals the atomic mass of that element. So if we had a mole of sodium, when you look at sodium on the periodic table, you've got the atomic number at the top, which tells you how many protons. And then you have the atomic mass at the bottom. That tells you the mass of one atom, the atomic mass units, right? But if you express that in grams, then that is the molar mass. Here's a couple more examples. So we said the molar mass is the mass of 1 mole of an element. You're taking the atomic mass and expressing it in grams. So for carbon, the atomic mass is 12.01. That means 1 mole of carbon has a molar mass of 12.01 grams. Whenever you see something with an equal sign like this, it's an equality. And where there's an equality, you can write a conversion factor. Same thing with lithium. This is the atomic mass, 6.941. You slap a G behind it for grams, and suddenly you have the molar mass, which is 1 mole of lithium has a mass of 6.941 grams. But what do you do if you've got a whole compound or a whole molecule, what you do is you add everything up together. You'll definitely need your periodic table. In this molecule, we have 2 moles of carbon. That's what that subscript means. 2 atoms in 1 molecule, or 2 moles in 1 mole. 2 moles of carbon. The periodic table tells us 12.01 for its atomic mass. We express that in grams. 12.01 grams becomes the molar mass. We're trying to end up with the number of grams of carbon in this molecule. So we put the grams in the top. And we do the same thing for each of these. Depending on the periodic table that you use, you'll either see 16.00 or you'll see 15.999. Same thing. You'll get pretty much the same answer no matter what you do. When you multiply it out for the first one, you're doing 2 moles times 12.01 grams over 1 mole. The moles cancel, and you're left with grams. So that's how much carbon is in 1 mole of this molecule. Next, we look at the hydrogen. There are 6 moles of hydrogen in 1 mole of this compound. Moles cancel. We get grams. There is no subscript for the oxygen, so we've only got 1. Now we have to add it all up because we need the molar mass of the entire molecule. So you figure out the contribution from each element, in this case the carbon, the hydrogen, and the oxygen, and then you add them all up. When you do that, this is your answer. That's the molar mass. So calculating molar mass is pretty simple. But how do we use molar mass? And this is the last section we're going to cover before we end class. You use molar mass to go between moles and mass. So moles to grams you use molar mass. You can also do the opposite to go from the number of grams to the number of moles. So I'll show you an example of that. We already went over the conversion factors. We have the mass. You can write it as an equality. The example is more important. Typical table sugar packet, so table sugar is sucrose, contains about 4 grams. How many moles of table sugar are in each packet? This is the chemical formula. Rephrase the question. We've got 4 grams of sugar. How many moles? That's what we're trying to figure out. I set up my question so that I can see what type of problem I have. I'm going from grams to moles, which means I have to use molar mass. The first step in this problem is to calculate the molar mass. So that's what you would do to calculate the molar mass. You'd figure out the contribution of each of these, and then you add them together. You want to make sure that you can do this. And if you want to string it all together in your calculator, you absolutely want to use parentheses. So I would put parentheses here like this, and like this, to make sure that you're getting the multiplication done first, and then you're adding the products of all of those. When you add all that up, change back to black here. You should get 342.34 grams. So 1 mole of table sugar is equal to 342.34 grams. That's our equality. Now we can set up our equation. And we're going to need the correct conversion factor. Since we're starting with the number of grams, and we're trying to get to the number of moles, we need to cancel out grams. So grams needs to go in the bottom. Moles will go in the top. So what you're doing in your calculator is taking 4 and dividing it by your molar mass. It's going to be a small number. So that's how you go from grams to moles using molar mass. I have one more example. I'll fill that out and make sure that it's in the notes. But we're kind of where we're going to pick up with chapter 7 is 7.7, which is where we're going to be doing more of these types of calculations. So I'll make sure everybody gets it. Okay. This map will help you if you know what you're starting with and you know where you want to end up. Then you can go through and figure out which you need to use, molar mass or Avogadro's number, to get there. So I definitely recommend using this chart if it makes sense to you. So here's your reminders. You've got an exam. It'll be available today, 5 o'clock. Make sure that you start your exam by 11:59 p.m. on Saturday, March 20th. If you need emergency office hours tomorrow, you need to let me know today, as in now. Send me a chat message, or you can wait until people start leaving and you can hit me up. But if you don't tell me now, there's no guarantee that you'll be able to get what you need tomorrow. Your Chapter 6 Mastering Chemistry is due on Sunday, so you've got some extra time. Normally it would have been due yesterday, but we didn't even talk about it. So I thought that was unfair. Hopefully the few extra days will allow you to do a little more studying for your exam, get your exam out of the way, and do Chapter 6. Your Chapter 7 Mastering Chemistry will not be due until the 31st. We haven't finished covering Chapter 7, so it's not due yet. If you happen to have some time between now and when we have class again, I would encourage you to at least look at the Chapter 7 assignment and see if you have any questions. Bring those questions with you, and just on the stuff we covered. If it's like, man, we didn't even talk about this, that's okay, because we probably didn't cover it yet. But bring your questions. And just to get you ready, your next exam will be April 1st. It's not an April Fool's trick. It just happens to be on April 1st. And it's going to cover 2 chapters, Chapter 7 and Chapter 8, both of which are pretty math intensive. So I'm giving you the heads up now. Make sure you do what you need to do to get caught up with Chapter 7 and stay caught up through Chapter 8. Because if math is a struggle for you, this next exam, after exam 2, will be hard. It doesn't have to be, but get the help you need on the front end so that exam 3 goes better. That's all I have for you. If you don't have any questions for me or anything like that, you're free to go.